Which style do you prefer? This one? Or I need to turn on the light? Very nice. Okay. Okay. Let's start. So first, I made an announcement on the Canvas, giving you a few suggestions about how to debug your machine learning algorithms, or like AWS or random forest. So because that arises from a few very useful and good discussion in my office hour. So first, be aware that the performance of any classifier or regressors are also dependent on data. And so you cannot get like 100% accuracy on garbage data. So if the results are not as promising as you expect, don't be scared. Don't be scared. So sometimes if the data is hard, for example, AWS, some student came to my office and asked me why the training error does not go to 0. Well, oftentimes we say the training error of AWS goes to 0, but that does not mean every data set the training error goes to 0. What you need to do is to ensure that your general behavior of your implementation is consistent with what we have discussed in our class, like your training error keeps going down to some level, right? And then your test error won't looks like a typical overfitting behavior. So test error, if just like something like this and keeps stable, that's good. But if when the training error goes to below some threshold and then jumps up, then that'll be problematic. Okay. And also, oftentimes we say like AWS is much better than any single decision tree or whatever, right? But it does not guarantee that it will always outperform fine-tuned single decision tree. But usually you should say your AWS should be better than many decision trees. But if you carefully tune decision trees, there's no guarantee that AWS will always largely outperform. So yeah, so just to give you a hint, like don't be bothered that if you don't see like excellent performance on that. And also I'm giving you a hint about how to debug your code, right? In addition for those white box tests, right? You should read your line, check each line of your code, and to ensure you have implemented every map, right? But also you can start with some very small number of examples. Right? So if you have only 10 examples, you should expect your AWS to have 0 training error. Or you can stimulate a few examples manually. And then if you think on those small or tiny data sets your AWS works well, and then you can try to test on larger data set. I give you, if I'm not wrong, the training example should be 5,000, right? It's very large, and you only have 16 features, so it's likely that it won't give you 0 training error. Okay.
This is just a question about the Kaggle competition. When did you say like the first cutoff was for if you're in like the top, you get some sort of extra credit? When is that first date?
I think it should be the midterm. In midterm, correct me if I'm wrong, because everything is on the website. So in midterm, if you got like, I guess should be top 3, you get actual, I forgot the number of donors. And in the final, before the final exam, we close the competition. Top 10 should get bonus points, but I forgot the actual points.
Even if only like 12 people are doing the Kaggle competitions, the top 10, or would you then like size it?
I initially expect that a lot of students will come to the Kaggle, but if we only have 10 students on that, that doesn't make sense. I will adjust accordingly. 12 might be, I mean, if there are only 12, I might adjust as well. But yeah, I haven't counted how many of you choose to the Kaggle.
One question from bagging. In bagging method, we have to take samples from the training data set. Yeah.
Yep.
Is it different how many samples we take each time? For example, from as you said, we have 5,000 data set, data point in data set. How much the size of each sample?
Oh, if in our problem we haven't in our problem setting we haven't like explicitly says how many data set samples you should choose, right? That means we use the default setting. That means you use Bootstrap. Bootstrap means that you select the same amount of training set randomly. Like you have 5,000 training samples, right? Then you random sample 5,000 again. Of course, all of those 5,000, many of them are duplicated. Does it make sense? Yeah, that's the original. Algorithm framework for bagging. Like you create the same size of you sample a Bootstrap data, right? Bootstrap data means that okay, I'm gonna randomly with replacement generate the samples, right? But the number of samples are the same as the original number of training samples. But they're not necessarily identical because every example when the sample it was put back and be sampled again with the same chunks, right? So there are some duplications of that. Another question? Okay, great. Yeah, if you have more question regarding the homework, and don't hesitate and come to the office hour or ask on cameras. But personally, I prefer you guys to come to the office hour because if you post a question on weekends, probably won't get immediately response. Okay, so let us continue with the perception. In the last lecture, we have introduced the details of perception algorithm, right? So briefly review, perception is kind of online algorithm. So it sequentially processes the stream of the training examples, right? And in the same, meanwhile, it's kind of lazy updating protocol. So for every training example, that means every pair of the input assign the label yi, right? So I will first use my current weight vector to make a prediction. So this is my prediction rule, right? So if my prediction is correct, I do nothing. I just look at the next example. Only when I make mistake, I make the update, right? The updating rule is like this, right? So I add the current weight vector by a learning rate multiplying with the product between the ground truth label and the weight vector. Okay. So we have explained why we should update like that, both in mathematics and geometry view. So those are, I don't think we need to go through it again, right? So And then we talk about the guarantees about perception. So this kind of greedy-based approach seems like unreliable on our vast, but the fact turns out not like this. Right? So we have two theorems that can characterize the behaviors of perception algorithm. First, if your training set, if your data set are really linearly separable, then perception always guarantee that you will find a separating hyperplane, a perfect classifier, which correctly predicts every example. That's called convergence theorem. But what if your data is not linearly separable? Right? You cannot find any lines or hyperplane which separates positive examples from all the negative examples. Then perception will enter into an infinite loop. Right? It just goes through a bunch of distinct vectors, distinct weight vectors, and cycle and cycle. Right? Never end until you force it to start. It's called cycling theory. So to characterize the to describe the behavior of perception, we introduce a very important concept called margin. So what is margin? First, we can define margin for a hyperplane with a data set, with respect to a data set. So when we say a hyperplane has a margin for a data set, it means that first, the hyperplane indeed separates the data set. If the hyperplane does not perfectly separate all the positive examples from negative examples in this data set, then it does not have a margin. Okay? Just like you cannot put 0 in a division. The same thing. We do not talk about margin for a non-separated hyperplane. Okay? And then if the hyperplane separates all the positive examples from negative examples in this data set, then the margin of this hyperplane with respect to this data set is defined as the distance, the smallest distance between the points in this data set and this hyperplane. You just compute the distance between every point and this hyperplane in this data set and pick up the smallest one. We mentioned the meaning of this hyperplane, right? And then we can generalize the definition of hyperplane of the margin to a margin for a particular data set. So what is margin for a data set? This is important because we're going to keep discussing margin and how is it related to the general performance. So we should be familiar with this concept. So what's the margin for a data set?
Possible margin and classifiers.
Yes. Right. So the margin of the data set is the maximum margin possible for that data set using any hyperplane or big vector, right? So just so look at this data set. So first it's linearly separable, and you can enumerate all possible separating hyperplanes, and for each separating hyperplane is associated with a margin. So pick up the maximum margin as the margin for this whole data set. So what's the meaning of a margin for a data set? What does a margin of the data set reflect or imply? We discussed it in last lecture, right? Someone forgot?
No, I wasn't just commenting on what I said it myself.
Yeah, feel free to share.
Well, I guess I just think about it as it's not necessarily well in this case it's literally is distance, but I just think it's this just in general the separation between positive and negative labels.
Yeah, exactly right. So you can imagine that the larger the margin, the farther away the positive examples from negative examples, right? So actually the margin of the data set indicates separability of the examples inside data, right? The separability actually indicates the hardness to classify the examples in the data set, right? So the farther away, the larger the margin, the farther away between these two types of examples, the easier they are classified by some linear classifiers, right? So later we'll discuss how margin affects the generalizability of linear classifiers. And then we define distance, right? So this is a formula, right? This formula, and for a general hyperplane H, and we can calculate any point in the same space, the distance between that point and this hyperplane. Right? What you need to do is just compute the classification function, which defines this hyperplane, and take the absolute value and divide it by the norm of the weak vector. So, when we discuss about the perception, we usually augment features. We augment the feature with 1 so that we can fold the bias term into the weak vector W. So that means our hyperplane, in our augmented feature space, our hyperplane is simply this inner product being 0, right? So apply this formula, we can compute the distance between the data point x0 and h in the augmented feature space as this, right? So someone asked me last lecture, right? When we consider or when we calculate distance in the augmented feature space, do we maintain the distance? So suppose x0 previously stayed in the original space, right? So we explicitly use the bias term and also the weak vector to compute the distance, right? So now I'm gonna augment x0 with some constant feature 1 and also augment w. I fold b into w, right? So in augmented feature space, we calculate the distance again. So will the distance remain the same or different? Different, right? Because here the weak vector changes, right? So numerator is the same, because if you unfold b out of w, the two numerators are the same, right? But in the denominator, we actually use the norm of augmented w, right? So it's w squared, norm of w, square norm of w plus b squared, right? If you compute it that way. So actually, the distance is not maintained when you do the feature augmentation. So be aware of this subtle difference. If you want to have a more concrete example, you can imagine. You can just do some derivation on paper. Right? Suppose originally your x just stay in one-dimensional space, right? Then your hyperplane is just a vertical line. You can compute the distance, and then if you do the augmented feature space, you're dealing with everything in a plane, right? It's two-dimensional space, and all the inputs examples are staying on a horizontal line with intercept being 1. Then you can try to compute the distance. It's different. This is some kind of subtle point. Don't confuse at this point. Okay. And then we can talk about the so-called mistake bound theorem, right? Which characterizes how many mistakes our perception learning algorithm at most makes to find a separating hyperplane. So basically, we assume our training set is a sequence of m input-output examples. So x1, y1, x2, y2 to xm, ym. So we first require that the feature vector, each feature vector, its norm is upper bounded by some constant r. That just means, okay, your feature values are normal. It's not weird values like infinity, negative infinity, or n, some kind of things, right? And then the second assumption is about the separability, right? Separability means that if there exists a unit vector such that for some gamma, some positive gamma, for every pair of training example xi, yi, we have this inequality. So yi times inner product between u and xi is no less than gamma. So what does it mean? Because u is a unit vector, right? According to the definition of the distance, here, the left-hand side is just the distance between u and xi, right? So it's just this is the classification function, right? U transpose xi times yi just to ensure, okay, this product is always non-negative. Then you should divide it by the norm of u, but u is unit vector, so you're actually dividing by 1, right? So this just says, okay, the distance between every point xi, yi, and this separating vector is no less than gamma. It means the margin is gamma, right? The margin of this separating hyperplane is gamma. Right? So basically, it says, okay, suppose there exists a separating hyperplane, and which are represented by a unit vector, and data is separable, and the gamma is a complexity parameter that defines the separability of the data frame. So anyway, it just tells you about the separability of this data set. And then with these two conditions, we can claim that the perceptron algorithm will make at most R or gamma square mistakes on the training sequence. So basically that you can repeatedly feed this sequence of data to your perceptual learning algorithm. It guarantees that the updates for this perceptron is at most R over gamma squared. And after maximum number of updates, it won't give you any updates. I mean, if you just keep letting the perceptron to see the new examples, always give correct prediction. Then you can stop, right? So everyone is comfortable, right? We're just reviewing what we have discussed in the last lecture. Right? So, and also we talk about like why we should introduce unit vector here, right? Just for convenience. If you hadn't been a unit vector, that means I remove unit here. If there exists a vector, right? There's no constraint that the norm of u must be 1, and this u vector satisfies that for any pair of xi, yi, this product is no less than gamma, and then our bound, mystic bound, should be skewed by the norm, the square norm of u. So we're going to discuss the details of this proof, and after that, there probably in the next homework you're required to show that the more general conclusion. If I do not put the unit here, how do you arrive at this? Okay. So here is the setting, right? So first and very important setting. Don't ignore that. We must initialize the weight vector W to be zeros. If you do the random initialization, it won't guarantee those bounds. Okay. And secondly, for convenience, we just set learning rate to be 1. And two preconditions. First, all training examples are contained in a ball of size R. That's kind of more intuitive description about the upper bound of the norm, right? So you can imagine in an n-dimensional space, the length of the input vector, the norm of the input vector actually indicates the length, right? So it just means, okay, the length of each input vector in the training set should be no less than R. So you can imagine there's a big ball, right? The big ball contains all the training examples in your data set. And second precondition, we have a unit vector U, which can perfectly separate data set, and its margin is gamma. That means, okay, for every pair of xi and yi, right? Every pair of xi and yi in your data, we have this yi u transpose xi is no less than gamma. So now let us look at how we derive this upper bound, right? Mystic bound, right? So we separate the proof into 3 steps. So the first step, we're going to show that a general claim. After making any t mistakes, the inner product between this unit vector u and the current bit vector wt is no less than t times gamma. Gamma, remember, gamma is the margin of this bit vector, right? So why should we use t to wt to index the current bit vector? Or in other words, why should we use number of mistakes? Why can we use number of mistakes to index the weight vector?
But in each step we update the W and the number of mistakes will vary.
Yes. Right. Let me repeat, right? So why we can use the number of mistakes made so far to index the weight vector? Right? Because the weight vector only gets updated when you make mistakes, right? If you don't make mistakes, you don't update. So you make the first mistake, you get first update, so you use W1, right? And you can keep looking at sequence of examples until you make the second mistake. Then you get second update, so you can index as W2, right? So that's why we can use WT to denote the current bit vector, because that means, okay, W has just been updated for t times. Okay, and then how can we show this conclusion, right? How can we show this inequality? Right? So we use induction, the strategy of induction. So in general, induction consists of 2 steps, right? The first step is called, anyway, you can switch the first and second, whatever. So the first step is assume that, okay, at any stage, your conclusion is correct, right? So I want to base on this conclusion to show at the next stage, the conclusion also is correct. This is called the generalization, right? And if that is proved, and then we'll look at initial condition, right? So initially, if at the very first step, the conclusion still holds, then you can induct, right? You can induct from the initial condition to infinite conditions, right? That's how we do the induction. So for any question, we're just reviewing the math, high school math, or I don't know, should be high school math, right? Okay, so let us look at we can first look at the generalization step. That means, okay, let us assume, okay, at some specific step t, we have this inequality holds. Right? And then we want to look at whether for step t plus 1, next stage, this inequality holds as well, right? This is the very first step. This is the first step of our induction, right? So we can take a look, right? So we want to say, okay, whether u transpose wt plus 1 is no less than t plus 1 gamma, right? That's the conclusion for the next stage. So to see that, we can first look into how we obtain wt plus 1 out of wt, right? That is according to the update rule of perception. So this is the update rule of perception, right? So if we make a mistake, then we're gonna get wt plus 1 by adding wt with yi xi. So remember here we set the learning rate r to be 1, right? So it's just yi xi, the product of the label and the input vector. So then we can represent wt plus 1 by the right hand side, right? So then we'll multiply u transpose individually. So get u transpose wt plus 1 equals to u transpose wt plus yi u transpose xi, right? Now, based upon the conclusion for the step t, right? So we have this one holds, right? But the K is look at the extra term, yi u transpose xi, right? So this term, from this term, can make us to connect to the precondition we just mentioned, right? So we know that, okay, U is a separating hyperplane and has a margin gamma. That means for any pair of xi, yi in your training set, you have this yi u transpose xi no less than gamma, right? So now we can say yi u transpose xi here, right? We just plug in the right hand side, the margin here, right? Because the data is separable by the margin gamma, we immediately get the extra term is less than gamma, and then based upon our assumption that the stage at step t, the equality holds, right? So we can immediately get like u transpose wt is no less than t gamma plus gamma is t plus 1 gamma, right? So we have u transpose wt plus 1 is no less than t plus 1 gamma. That means, okay, if I assume, okay, at stage t, this equality holds, then at stage t plus 1, this equality holds as well. We finished the first step, first proof step, generalization step in the induction. Does this sound? Is everyone on the same page? Now, assuming it's kind of straightforward, right? If you just follow how they arrive at this point, right? So now the next step in the induction is to look at the initial step, right? The initial step is that, like, at the very beginning, W0 is 0, right? Because we initialize our weight vector to be full of zeros. So W0 is 0, and then U transpose W0 is 0, right? And obviously we can do one more step, right? So if we make the first step, if you make the first mistake, so we're gonna add W0 with yi xi. And we know yi xi, and then we do this inner product between U transpose and W0 plus yi xi. So here is 0, right? And you only have yi u transpose xi, which is no less than gamma. So you can immediately get that u transpose w1 is no less than 1 gamma. Right? And then we'll finish then we show that, okay, the initial the inequality for the initial stage is also correct, and also then you can induct, right? You can induct to many steps, whatever infinite many steps you want, right? Okay, any questions so far? We might go through this proof a bit too quickly in the last lecture, so I'll look at it again, right, to ensure everybody is on the same page.
Is there any practical usefulness for the gamma?
Practical usefulness for what?
For the gamma.
For the gamma.
Yeah.
No, it's just to help you to analyze how many mistakes your perception will make. In other words, like how long your perception will take to run. Later we'll give you some examples to estimate the number of updates your perception need. Okay. Okay. So now we finished the proof for the first claim. Right? So we're gonna prove the second claim. So the second claim is that after any arbitrary number of mistakes, like t mistakes, we can show that the square norm of the current weight vector is upper bounded by t times r squared. So remember, r is the maximum length of the input vectors, right? So how can we arrive at this point? Again, we use the induction. So in the first step, let us assume, okay, for any stage t, we have this upper bound to be correct, right? And then we'll look at the case of t plus 1. So to look at this case of t plus 1, we would like to look at the square norm of wt plus 1, right? So again, according to the updating rule, wt plus 1 is wt plus yi xi. So you take square norm, so you can expand the square norm, right? So it has 3 terms. The first is square norm of wt itself. The second is square norm of this yi xi, right? But yi squared is always 1, no matter y is more 1 minus 1, right? So I have the second term. And third term is a cross term, right? This is 2 yi wt transpose xi. And we can look at those terms, right? So first, the rightmost term, right? The square norm of xi. According to our first precondition, the length of each input vector is upper bounded by r, so we immediately have xi squared, norm of xi squared is upper bounded by r squared, right? And the second thing is pretty interesting. So we know that we make this update to arrive wt plus 1 only when we make wrong prediction on xi, right? That means this term must be a negative, right? We mentioned that, okay, how can we test whether we make a correct prediction now, right? We just look at whether this product is positive or negative, right? If you're correct, okay, it must be non-negative. If it's wrong, then y is 1, then this classification function value is negative, right? Or opposite sign. So this product must be negative. And again, because we only update our model when we make mistake. So we use WT. When we use WT, we must make wrong prediction at this example, right? So this middle term must be negative. That means it must be less than 0, right? So you have a upper bounded for this right hand side. R squared upper bounded by the square norm of xi, right? And WT squared is upper bounded by what? Yeah, TR squared, right? According to our assumption that at stage t, the upper bound is correct, right? So then we can immediately immediate successfully induct at t plus 1, right? So at t plus 1, then we have the square norm of wt plus 1 upper bounded by t plus 1 r squared, right? So the first step for the induction is proved. Right? And the second step is to look at the initial step. Right? Initial step is when w0 is 0. So you say, okay, t is 0, left hand side 0, and right hand side 0. Right? So you can check one more step. Say, if I make update, whether I have a w1 squared less than or equal to a t1 r squared. Right? This is pretty straightforward. So now I have shown that. What I'm showing the second claim. So any questions so far?
So it's actually just very confusing. Why the last term xi squared? Why not the xi yi squared?
Why not what?
Why not the xi squared multiplied xi?
yi is 1.
Y is 1.
Because it gets squared whether it's plus 1.
Yeah, yi is either 1 or minus 1, right? So this is essentially yi times xi squared, right? So it's a constant. You can take yi out and take squared. So it's y squared, but y squared is always 1. This is a setting for our linear classification. We assume your label is either 1 or minus 1, right? Any other question?
But for induction, don't we have to show that w sub t plus 1, the norm of that squared is less than t of r squared, but it looks like at the bottom we get that it's less than t of r squared plus r squared.
I didn't get the point. So
Don't you have to show that your t plus 1, wt plus 1, don't you have to show that that is less than tr squared? for induction? Or am I confused?
No, we first assume that, okay, at t, you have this hold,
Right.
and then you have to show that at t plus 1, you have this one less than or equal to t plus 1 r squared. So this is the first step. It's called generalization step in the induction, right? So, of course, you can assume, okay, this is at stage t minus 1, I have this. And then at stage t, I should have a wt squared, norm squared less than equal to tr squared. It depends. Someone likes to generalize from t to t plus 1, and someone likes to generalize from t minus 1 to t. It's just custom. It doesn't matter. Any other question? All right. So now we have two conclusions, right? So first, after t mistakes, meaning that after t updates of your perception, we have the inner product between your unit separating bit vector u and wt lower bounded by t times gamma. Right? Gamma is the margin of u, right? And also after t mistakes, we have the square norm of the current bit vector upper bounded by t big R squared, right? So the next step, the final step, is to connect them together. If we can successfully connect them together, and then we might solve the upper bound of t. Remember, t is the number of mistakes, right? So how can we do that? So we first look at the second form. Right? So if we just switch the direction of the inequality and take the square root on both sides, we obtain that, take square root, right? We have r, big R, square root of t is no less than the norm of wt, right? So, and the second step is very important. We can show that the norm of wt is no less than or equal to, no less than the inner product between the unit vector u and wt. And here we use the so-called Cauchy-Schwarz inequality. So how can we memorize Cauchy-Schwarz inequality? From the geometry. So for any two vectors, right, no matter in arbitrary dimensional space, right? So if you want to compute the cosine of the angle between two vectors, how can we do that? There's some formula, right? The formula says that, okay, the cosine of the angle between two vectors, say u and wt, right, is equal to the inner product between these two vectors divided by the product of their norms. This is just definition. And obviously, the cosine value is always between 1, minus 1, 1, right? So that means this inner product is always less than or equal to the product of the norms, right? If it is negative, it must be less than, right? If it is positive, then because it's less than, cosine value is less than 1. Right? So the inner product is always less than or equal to the norm of the first vector times the norm of the second vector, right? And here we have a special case that we require that the vector u is unit vector. So that means the norm of u is simply 1. And then we immediately get that the inner product is less than or equal to the norm of wt. It's just the application of this Cauchy-Schwarz inequality. And then we have a norm of wt is no less than u transpose wt, right? So now we can connect to the first result, right? So we know, okay, this inner product is further lower bounded by t times gamma. And now we just look at the left-hand side and right-hand side, right? So we have r square root of the number of mistakes t is no less than t times the margin gamma, right? So just to solve this, we obtain that T is upper bounded by R squared or gamma squared. So we finish the proof. Any question?
So can you go back to the last page? So what about the angle is larger than 90 degrees? The cosine should be negative. Yeah, I mean the angle.
The cosine.
Yeah.
I mean cosine is negative.
Yeah.
Yeah, the cosine is negative. Then U transpose WT must be negative, right? And then it must be less than U normal U times normal W, because this product is always positive. If the angle is less than 90 degrees, okay, then this value is between 0 and 1, right? So also still the U transpose WT will be less than or equal to this product. Any other question? As long as everyone generally follow the flow to show the proof, that it should be good. But later, there will be a few homework assignments to help you reinforce those procedures. Okay. So now we have bounds the total number of mistakes. In other words, bounds the total number of updates when you train a perception in a linearly separable data set. So now let us review this Misty-Bound theorem, right? So basically, Misty-Bound theorem tells that under the ideal case that your training data is linearly separable, how many mistakes at most your perception algorithm makes during training procedure, right? So basically, it assumes that first, the input vector, every input vector in your data set, its length is upper bounded by some value R. And second, there exists some unit vector which can well separate your data set. Of course, if your data set is linearly separable, such unit vector must exist, right? And then it has associated margin gamma. Then we can claim that the perception algorithm will make at most R over gamma squared mistakes on the training sequence. But it does not mean it will make exactly this number of mistakes. Actually, this is a quite loose upper bound. It's just indicative to show how difficult to train a linear classifier, train a perception to separate data set. So we can view this, we can analyze it through some geometry interpretation, right? So suppose this is our data set. So positive examples, negative examples, right? So first, to estimate what's the most number of mistakes, or what is the most number of updates to train a perception. Right? So first, we're going to find the upper bound for the length of vectors R, right? So how can we do that? We just look at how far away each input instance to the origin, right? We just look at the furthest point and use that as the radius to draw the ball, right? So this ball actually includes all the training examples in your data set. And secondly, I'm gonna find an arbitrary separating hyperplane. U, right? Of course, we need to normalize the weight vector U such that it is a univector, right? And then we can look at the margin of this U vector. So it's gamma here. So now with R and gamma, we can claim that okay, when I use perception to learn a linear classifier, the number of mistakes is upper bounded by R squared over gamma squared. So now let us try to analyze according to this upper bound. Right? So first, what does big R mean in your training of perception?
number of mistakes can be increased.
Yes. Right. So the larger the span of the whole training set, or larger the spread of the whole training set, the more likely you make more mistakes, right? Because you have a larger upper bound. Because R is larger, right? And secondly, how does gamma affect the training?
The smaller gamma, the more mistakes.
Yes. As we mentioned, right? Margin actually indicates the separability of the data set. The larger the gamma, the easier for us to separate the data set, right? So you can imagine, like, if this positive example and negative examples are separated quite far away, then the number of mistakes, the upper bound number of mistakes is relatively small, right? That means, okay, it's easier for you to train a perception to separate data set. But on the contrary, if your training examples, your positive examples are quite close to negative examples, such that your gamma is pretty small. So you can imagine the bound becomes large because it's proportional to the inverse of gamma squared, right? That means you potentially will make a lot of mistakes to find a right separating hyperplane. So although this bound is kind of loose, why it is loose? Because you can find arbitrary separating hyperplane and use that gamma to estimate the bound of the mistakes, right? So this is quite loose, but it is also indicative about how difficult you train a perception. Okay. Mm-hmm.
When the data set is linearly separable, then number of mistakes should be 0 after running the algorithm. Yes.
Yeah, of course. After making a certain amount of mistakes, you can predict every training example. That means you find a separating hyperplane.
So this theorem thus is for the data set that is not linearly separated.
This theory is just for a data set that's linearly separable. If it is not linearly separable, we won't have such bounds. And actually, the number of mistakes is infinite. You're entering into a cycling stage, right?
So the number of mistakes is bounded by that number, but when the data is separable after running the algorithm, we will get no mistake.
Mm-hmm.
So this shows, I don't know, this shows in which stage this is the number of mistakes. In each object, you mean? Yeah.
No, throughout running.
Total.
Throughout running, just like, suppose that you do not intentionally stop your perception, right? You just run it forever. And how many mistakes you make at most? Of course, you can count, right? You can look at whether it can correctly predict all the training examples. If you find, okay, it has already been able to correctly predict all the training examples, you can stop. But if you just let run forever, you say, okay, after a certain amount of examples which are bounded by this, it won't make any update. Okay? You have a question?
No.
All right.
So I was just wondering how to calculate the unit vector u, or is it just a random?
You can just pick up any.
You don't like the straight line.
Yeah, as long as it has non-zero gamma.
Oh.
If the gamma is zero, then it doesn't make sense.
Gamma is dependent on the unit vector picture.
Yeah, of course, it depends on the position, right? Unit vector. So that's why I mentioned it's quite loose bound, because any arbitrary separating hyperplane will give you a reasonable bound, right? And another thing you should be aware that if I use this separating hyperplane to give you associate with this gamma to give you this bound, it does not necessarily mean that your training of perception will end up with the same hyperplane. It might end up with another hyperplane. It depends on how the order the order of the training examples you fit to the perceptron algorithm.
So, like, let's say you just had 2 points on a line, just one dimension, so R is just 1. And then let's say they're just like one unit apart. Then it's just 1 over 1. Does that mean that one mistake is like first it thinks this is positive, that's its only mistake? If like that's the upper bound, because then the next guess it's going to get right. Another one. Like just 2 points on a line, separated by 1, so your ratio is equal. The number of mistakes is 1.
I don't think you'll get only one, because R is R is a radius, right? R is radius, yeah, it is possible.
So, well, like in this case, R is just the number of features, right, in your vector. So a point would be the same as R equals 1. If this was just a point in one dimension, just on the one line, X line, then R would equal 1 in that case, right? Because that's the number of like dimensions essentially of your input vectors. So then you just have 2 points on a line, and the distance between them is 1. So then your number of mistakes is upper bound by 1.
Yeah.
So is that one mistake that you can make, that upper bound is just saying like, okay, I think the point on the left is positive and maybe it's wrong, then it switches. So
Yeah, in an extreme case, yeah, that is possible. Any other question? Okay, hopefully this theorem can give you.
I was just going to ask if this like applies in this case at all, but if you have more inputs such that you have like a 3-dimensional graph or like a tensor like several dimensions, do you need to add more variables to this equation, or is this just for like the 2D case here?
No, this is for a general case. Like R here is the length, the norm of the input vectors, right? So no matter how many dimensions your feature vector has, you can calculate the norm on that, right? So R is upper bound of the norms, length.
When we are given a data set, is there any test before going to run the perceptron algorithm?
It's really very hard to show the data set as linearly separable. Unless, like, for example, if you just run perceptron, and after a certain amount of time, you say, okay, it stops. It won't need you to enforce your perceptron stop. Then, of course, you can show it's a linear separable. Or you can train with any other linear classifiers. You end up with like 0 training error. Of course, it is linear separable, right? Another question? I hope this figure will help you understand this theorem. What does this theorem reflect, right? To give you a more intuitive understanding of that. Right? So now, to give a more concrete understanding of this perceptual mystic bound, we can do some exercise. So first exercise would be like, how many mistakes will the perceptron algorithm make to learn a classifier for a disjunction with n attributes? Of course, each attribute is Bloom, right? So the training data set we assume like consists of all 2 to the power of n Bloom input attribute vectors in instance space. So suppose our target function is just a disjunction function. It's disjunction of n Bloom variables, right? And our training data sets consist of all possible n-dimensional Bloom input vectors. So now we want to train a linear classifier with perception. How many mistakes does perception make at most? So first I want to ask, do we have is this disjunction with n Bloom attributes linearly separable? We discussed it before, right? If it is not linearly separable, then the number of mistakes you made is infinite. right? It's infinite. It won't converge, right? So the second question is, how many mistakes will the perceptron algorithm make for k disjunctions with n attributes? So if I just pick up k variables, all of its n attributes, and to form a disjunction IP, and we still have like 2 to the power of n training input vectors, how many mistakes for a perceptron to make to obtain a linearly separable hyperplane? Let's try to use the theorem we just derived. Right? So first, this is conjunction. Let's look at the first exercise, right? The conjunction function is x1 conjunction with x2 until xn, right? So first, this one is linearly separable. We have discussed this before, right? And as to which linear classifier it is equivalent to, we'll discuss in a minute. Right? So first, to apply, let us consider how to apply this mystic bound theorem, right? To apply mystic bound theorem, first we need to know what is the upper bound of the norm of the input vectors. So what is the upper bound of the norm of the input vectors? Remember, we have an n-dimensional Bloom features, right? So what's the maximum length of your Bloom input vectors? Or in other words, which training data point or which input vector is farthest from the origin? Any suggestion?
The vector with all ones.
Yes, the vector is all ones, right? And then but here you should be aware that because when we talk about perception updates on the theorem, we're doing everything in augmented feature space. That means each feature vector is augmented with 1, right? And also in this augmented feature space, obviously the farthest point from the origin it still consists of all ones, right? Then your distance, the distance between the farthest point and the origin is just the square root of 1 plus n, right? You can imagine it's 1, 1, 1, 1, all of them are ones. Then the norm is just the square root of n plus 1.
Why 1 plus 1? Why is it not 1? N.
1 plus n.
Yes, you have n ones, so it should be the square root of n.
Oh, I just mentioned, like, we're talking about everything in the augmented feature space. Yeah, we should augment the original input vectors by 1, right? So actually, in augmented feature space, all of the input vectors are in n has n plus 1 dimensions, right? And of course, still the farthest point, the longest vectors have every element to be 1, right? So we have the upper bound, the maximum length of the input vectors to be a square root of 1 plus n, right? Every attribute takes 1, and we augment the constant feature 1. So we get our upper bound of the norm of the input vectors, which is this, right? Square root of 1 plus n, right? And next, we need to find a separating hyperplane, unit vector separating hyperplane with some non-zero margin gamma, right? So how can we do that? That refers to how we construct a separating hyperplane for this disjunction, right? So we use the trick we have discussed before. So the conjunction is 1 if and only if there is at least one variable being truth, right, or being 1. So we can express this condition as their summation is less than 1, right? And then we immediately get a linear classifier, which is x1 plus x2 to xn minus 1 equals to 0, right? So now the question is, can we use it to get margin? Can we use it to get a gamma in our mystic bound? An idea?
it shows gamma is at least 1.
At least 1? So you mean we can use this, it's feasible to use this classifier as our separating hyperplane and obtain the gamma?
Yes. Using the origin in the equation of hyperplane, we get 1.
So you mean the gamma for this is simply 1? Okay. Yeah, sounds intuitive, but is there any other suggestion or comments? Or you want to change your?
No, it's, we have to find the distance between hyperplane and the origin.
It's not necessarily the origin. But I think you actually reached the key point here. Right? So be careful. There's a trap here. So as we mentioned, right? So when we find the number of mistakes, the upper bound number of mistakes, we need to find non-zero gamma, right? If the margin is simply 0, then the upper bound is infinity. It's meaningless, right? Of course, it's correct, but it's meaningless. Then we should look at what is the margin for this particular separating hyperplane, right? So what is the margin for this? So what's the definition of margin?
You have to find the distance of each point from the hyperplane.
Yes. And we'll look at the minimum distance, right? But what if there's some point which strictly, directly stay on the hyperplane? What's the margin? Margin becomes 0, right? But do we have some points in the training set which just lies on this hyperplane?
Yes. There are endpoints.
Yes. Yes, right? So if we set just x1, x2 to xn all be 1, then this point just stays on the hyperplane, right? So margin is simply 0. That means we cannot directly use that, right? It's not simply, sorry. It's as long as one element in this n variables are 1, this equation is 0, right? That means, okay, I'm gonna stay on this, I'm just lie on this hyperplane. So the margin is simply 0. The minimum distance, right? Minimum distance now is 0, right? So then we need to switch to another separating hyperplane, right? At least with non-zero margin. Otherwise, we won't have like meaningful mistake bound. How can we change? How can we change our linear classifier?
Using 1/2 instead of 1.
Yeah, that's one solution, right? And actually, there are many solutions. I just move this a little bit, right, so that I can move away from those points which originally stay on the hyperplane, right? So one choice will be just move to minus x1 plus x2 to xn minus 1/2. We can check whether there are no points stay on this hyperplane directly or not, right? So first, if all x1, x2 to xn are 0, what's the classification function value? It's just minus half, right? So it won't stay on the hyperplane. Oh, by the way, if you want to test whether the point stay on the hyperplane, just look at whether this classification function value is 0 or not, right? So for full of zeros, that point won't stay on the hyperplane because this value is minus half. But for what about other cases?
Okay, so integers, but 1/half is nothing.
Yes, exactly, right? So remember, no matter how you choose, how many ones you choose among x1 and xn, right? Their summation must be some integers, right? So subtracted by half, it must be positive. unless you set all x1 to xn are 0, then that would be negative. That would be minus half. It's another non-zero values. So in this way, we see that no points will lie on the boundary. Does it make sense? Everybody's comfortable? Okay, then we can look at the margin for this hyperplane, right? So what is the margin for this hyperplane? Which point is closest to this hyperplane? The one, either you can pick up all x1 to xn to 0, or just set one element to be 1, right? Then their value is just, their function value is just half, right? And then divided by the norm of the weight vectors, just as the minimum value. If there are more than one elements among x1 and xn to be 1, then this function value is bigger than half, right? So the distance is bigger. So that means first we find the closest point to this hyperplane, right? Second, we need to normalize the weight vector to ensure this hyperplane, the weight vector is unit vector. So it is pretty easy to normalize. You just divide the weight, the coefficient in front of each x1 to xn, and its bias term by their norm, right? So this is a u vector, and this is x. This is our separating hyperplane, and then to compute the margin, we just pick up the point which is closest to this margin. That means all attributes being 0, or only one attribute is 1, right? So then we can compute it. We just say we can pick up all attributes to be 0. So the input vector is simply 0, 0, 0 until the last element to be 1, right? You substitute for x1 to xn here, right? You get half, or 1 over half, divided by this square root of n plus 1/4. Okay. So get gamma, right? Everyone is comfortable? Right? Then now we immediately get the mystic bound, right? So I didn't show the result, but anyway, you have r here, right? You have r here. You divide r square, which is 1 over n, by this gamma square. You end up with the mystic bound, right? So we can follow the same procedure to estimate the number of mistakes. Upper bound of the number of mistakes made by perceptron for k disjunctions case, right? So just give you the concrete example, and the other problem is an exercise for you. So now I have a finished introduction of perceptron mystic bound. Right? Any questions so far? Okay, so, and the last topic regarding perception is about, in practice, how we develop that. That refers to a few variants. So, we're talking about how do we use the perception algorithm with a finite data set, and two variants. The first variant is called margin perception. The second variant is called voting or averaging perception. Those methods can further improve the robustness of perception. So they are popular in practice. So this is a standard algorithm. Look at it again. We initialize our weight vector to be full of zeros, and we go through the data set many times, right? So in practice, before we inside each iteration, we're going to first shuffle the data. So we won't keep the same order of the sequence. Each time we just randomly permutate the examples, and then sequentially fit to our perception algorithm. And if our current weight vector is making a mistake, then we update weight vector correspondingly. Otherwise, we just look at the next example in sequence. So when we finish the pass for one pass for the entire data set, we finish one epoch. So you'll see a lot of terms like epochs in the training of neural nets or whatever. Epoch just means, okay, when I pass through the entire data set once. That's how, in practice, you implement your perception. And then if you finish the running of the maximum number of epochs t, then you just stop and return the current bit vector delta. So obviously, the standard perception algorithm require you to set a hyperparameter, which is the maximum number of epochs. So again, there's no theory telling you how to set up this t. So basically, you should tune it dependent on the applications.
Why should we shuffle the data in each repetition?
Oh, that's a good question. So shuffle the data means that every time you stream the instances in a different order, right? So you're gonna train the perception in a more balanced way. It's more like if you feed the algorithm in a sequence as example 1, 2, 3, 4, and next time 1, 2, 3, 4, and the third time 1, 2, 3, 4. It's always like that. It will make it will very likely to make your weight updating into a very fast direction. So that's why people usually random shuffle data so that you have the chance to update the weight vector toward all kinds of directions. Any other question?
So you want to use the permutation of the data in this case?
Yes. Yes. So this is not only applied to training perception. Actually, in all kinds of stochastic learning algorithms, you're always using this kind of framework. Every time you just permutate data once and going through them with stochastic gradient set up. Any other question? So in the last minute, I want to discuss with you. This is an important concept, right? So suppose I have two sets of the examples, right? Positive and negative, and of course, because they are linearly separable, I have many choices of the hyperplanes, right? So I want to ask you, which hyperplane do you think is better?
One.
Why each one is better?
Margin.
Why margin is greater is better?
Less error. Less bound for error.
Yeah, it does have some bound for error. But what is the intuition, right? So everybody looks at a right intuition.
Just better for noise in the data set.
Less sensitive.
I mean, as your margin gets smaller, your probability of misclassified gets larger.
Yeah. I think all you said is correct, and that all your intuition is correct. But I just want to give you some kind of more explanations, trying to extend your ideas, right? So yeah, you're right. So among all those separating hyperplanes, we tend to choose the one who has the larger margins. Why? Because the larger the margin, the further away you're separating the classification boundary from the distance, from the instance. So what's the benefit that your hyperplane is further away from those training instances?
You have a smaller chance that maybe like a positive is going to be on the wrong side.
Yeah, exactly. Why? Because The further away you from those instances, that means you're further away from the high density regions. So remember why those examples appear here and here, right? Because they have a better chance to appear here, right? If you have a separating hyperplane which are close to these examples, that means you're gonna cross those high density regions. That means, okay, here, of course, if your negative examples show up here, it's fine. But they also have a high chance to show up here. In this kind of oscillation, you're gonna make a lot of mistakes, right? So similar kind of things apply for the positive examples. If you're too close to those high density regions, then you have high chance to have positive examples on both sides of the boundary. That means you're likely to make a lot of mistakes. That's why we always choose the separating hyperplane has large margins, right? Because they are far away from high density regions. It's unlikely that positive examples will show up here.
But does perceptron find the optimal hyperplane though, or does it just find a
No,
hyperplane?
no, there's no guarantee on that.
Yeah,
That's why we're
okay.
going to discuss the so-called margin perception. Does it sound right? Okay, so yeah, let us discuss a few variants in the next lecture. So see you on next Tuesday.